This video is about correlation and linear regression. The first part of the video will be talking about correlation. When we speak of correlation, it determines the relationship of two quantitative variables. To demonstrate, suppose you have two quantitative variables, x and y. Now, you want to determine whether an increase in x will also lead to an increase in y. Vice versa, will a decrease in x will also decrease in y? Or it may be that an increase in x will lead to a decrease in y, and likewise a decrease in x will lead to an increase in y. This shows that x and y may have the same direction, or x and y have opposite direction. Or maybe an increase in x, we don't know what will be the direction of y. And vice versa, will a decrease in x will lead to a certain change in y? We don't know. In this case, there is no direction. The measure, which is Pearson correlation, is a value which is between -1 and 1. If the value is positive, there is a direct relationship, meaning they have the same direction. Or the value of r is negative, meaning they have inverse relationship. This shows that they have opposite direction when r is negative. Now, how strong the relationship is, that is determined by the magnitude. R of 0, it means that there's no relationship, and as the value of r goes further from 0, meaning it gets closer to +1 or -1, the more perfect or strong their relationship is. Graphically, when the value of r is 0, this is x and this is y, take a look at the points seems like at random. But as the value of r gets closer and closer to 1, the graph gets closer and closer to form a perfect line. On the other hand, if the value of r gets closer to -1, likewise, the points get closer and closer to form a perfect line. Consider here that if r is positive, the line that they will form is leaning to the right, meaning an increase in x leads to an increase in y. As the value of x goes to the right, the points are going upwards. On the other hand, if the value of r is negative, the line that they will form is leaning to the left. Meaning, as the point moves to the right, or in other words, the values of x increases, the value of y decreases. Now, as a rule of thumb for interpreting the size of a correlation coefficient, here's a table showing the correlation value and its interpretation. A value of correlation from 0.9 to 1, there is a very high positive correlation. And as the value gets closer and closer to 0, like 0.3 to 0.5, there's a low correlation. Now, the estimate of the Pearson correlation may be computed using this equation. And for inference purposes, meaning you're going to conclude about the population using the sample, you're going to make use of this t-distribution with df of n-2. Note that the null hypothesis there implies that the value of r is 0, indicating no correlation or no relationship between the two variables. And on the other hand, your alternative hypothesis is that the value of the Pearson correlation r is not 0, meaning x and y are correlated. Now, to show you an example, suppose that a group of researchers wanted to determine if for patients who developed anemia, hemoglobin and MCV, which stands for mean cell volume, which is a part of complete blood count test or the CBC, are correlated. Test at 5% level of significance. So again, your null hypothesis here implies no correlation, and alternative hypothesis implies that there is a correlation between the two variables. In this case, the two quantitative variables are hemoglobin and MCV. So suppose this is your X and this is your Y. So plotting these points in a two-dimension coordinate system, we have these plots. So plotting these points, suppose we have 87.8 and 137. It's somewhere here and somewhere here. So this is ID number 1. ID number 2, we have 91.6 and 123. So suppose it's 91.6 and then 123. This point is case number 2 or ID number 2. So plotting these points will lead to this scatter plot. So for the null hypothesis, again, implying that there's no correlation between the two quantitative variables, your null hypothesis is that hemoglobin and MCV are not correlated. While your alternative hypothesis would be hemoglobin and MCV are correlated. Now, let's compute for the value of R. So take a look at the value of R. It requires the sum of the product of xy, the sum of x, the sum of y, the sum of x squared, and the sum of y squared. Now, if this is your x and this is your y, you will be needing the product of xy, the square of x, the square of y, and then all we have to do is to get their sum. So given these sums, let's substitute the values. So n here will be the number of samples, so we have 10. Sum of xy will be this one. Sum of x will be this one, 904.6. Sum of y will be 1,282. Sum of x squared will be 81,928.14. And sum of y squared will be 165,642. And then these two here are simply the square of the sum of x and the sum of y. Now, substituting those values and computing for the value of the estimate of R, we're going to have negative 0.9, which is a strong negative correlation between x and y. So since this is negative, this implies that as x increases, y decreases. Meaning, as the mean cell volume or the MCV increases, hemoglobin decreases. And vice versa, as this one decreases, this one increases. Next, for inference, let's compute for the test statistic, which is t. So all we have to do is to substitute the value of r as negative 0.9034598. The value of n is 10. And same value of r, but this time it is squared. So we will get a test statistic t of negative 5.961. For the degrees of freedom, it's just n minus 2, so that's 10 minus 2, we have 8. Now, for the critical value, since we made use of the t statistic, which is considered as a t-test, we're going to make use of this table. So with df of 8, and since our alternative hypothesis implies non-equality, then we're going to make use of two-tailed test. So with df of 8, we're going to have 2.3060. Again, since that is two-tailed, we're going to make use of the positive and negative value of t. Now, we may verify that in R using QT 0.025, 8 and QT 0.975, 8. Again, to illustrate this, since alpha is 0.05, then this is 0.025, and this is also 0.025. Now, QT here will be 0.025, which is the area to its left, indicating 0.025, then the degrees of freedom 8. Then to get this one, that's QT, and then, since this is 0.95, to complete the 1.0 area, then the total area from this point to this point is 0.975, 8. Now, negative 0.59 is somewhere here, which is in the area of rejection. So remember that these two are the areas of rejection. So since that is in the area of rejection, then we're going to reject the null hypothesis and conclude that there is sufficient evidence that then include the alternative hypothesis, hemoglobin and MCV are correlated for patients who developed anemia. Now, for the p-value, all we have to do is to get the area of negative 5.9 to the left and 5.961, since that is two-tailed, to the right. Now, this part is just pt negative 5.961, comma 8. And this one is 1 minus pt 5.961, comma 8. Again, the reason for this 1 minus is because the total area here is 1. And this quantity is just from this point to the left. So since the p-value is less than the alpha, which is 0.05, then we're going to reject the null hypothesis. So that's about the correlation. Now let's move on to what we call the simple linear regression, which some call it as the univariate linear regression. Now, in simple linear regression or the univariate linear regression, we're trying to form the equation which is y equals sum beta sub 0 plus beta sub 1 x sub 1 plus an error term which is the epsilon symbol. We're trying to correlate if this x is correlated with y. Now, in the previous example, we found out that there is a correlation between MCV and hemoglobin, having a correlation coefficient of negative 0.903, which rejected the null hypothesis. Now, our goal now is to find the best fit line, in which that line produces the minimum error, or what we call the minimum squared error. We also call this as the ordinary least squares. In algebra, you know that y is equal to mx plus b, in which b is the y-intercept and m is the slope. Now, all we have to do to find this equation is to estimate the beta sub 0, which is the y-intercept, and beta sub 1, which is the slope. And we may estimate those values using these equations. So, beta 0 is equal to this, and beta sub 1 is equal to this. Note that these are just estimates, so I'm going to put a hat indicating an estimate. And again, the epsilon refers to the error term for the residuals. Later, we're going to talk about that. Now, let's try to estimate first the values of beta sub 1, which is the slope, and beta sub 0, which is your y-intercept. Now, all we need are the sum of xy, the sum of x, the sum of y, and the sum of x squared. So the same values that we got a while ago, and substitute those values. So sum of xy here will be this one. Sum of x would still be 904.6. Sum of y will be 1,282. Sum of x squared will be 81,928.14. Now, substituting those values, we have negative 3.277. Now, to get the y-intercept, all we have to do is to substitute the same sums and then include the value of the slope as beta sub 1 hat. So, substituting those values, we have 424.633. Now, given these values, since this is your beta sub 1 estimate and this is your beta sub 0 estimate, then those will be the values of that in the equation, which forms the linear equation to be y equals 424.633 plus negative 3.277, in which y here again is your hemoglobin and x sub 1 is your MCV. Now, given the equation again in which y is your hemoglobin and x sub 1 here is your MCV, suppose we're asked to estimate the hemoglobin of a patient with MCV of 87.8. Now, all we have to do is to substitute this value as your x sub 1 to have an estimate of y. Note that when we estimate y, we ignore this error term first. So in other words, to estimate y, so I'm using y hat, all we have to do is to use this equation. Again, without the epsilon. So substituting 87.8 as your x sub 1, we're going to have 136.91 as the estimate of hemoglobin. Next, estimate the hemoglobin of a patient with MCV of 91.6. So similarly, all we have to do is to substitute 91.6 as the value of x sub 1. In this case, we're going to have 124.464. And suppose we're asked to estimate the hemoglobin of a patient with MCV of 97.9. So likewise, we're just going to substitute this value as the value of x sub 1. And we're going to have an estimate of hemoglobin which is 103.819. Now, since these are the estimates of the hemoglobin that we were able to compute given this MCV, consider here now that the actual values are for MCV, which is 87.8, it's not 136.9 but 137. Likewise, for a patient with MCV of 91.6, it's not 124 that we estimated, but it's just 123. Likewise, for a patient with MCV of 97.9, the actual value is not 103, but rather 104. Now, this shows that our estimate has some little errors. Now, those errors are the ones represented by the epsilon here. Since our estimate is 136.9 for a patient with MCV of 87.8, our estimate needs 0.083 to come up with the actual value, which is 137. So you add 0.083 here to reach the actual value, which is 137. Note that y here is the actual value. Now we have to add a little value to our estimate to reach this value. Value to be added or subtracted, we call it as the residuals. Now moving forward, let's have 91.6. Our estimate is 124.464. But our actual value shows that it's 123 for an MCV of 91.6. Now what do we do to get the actual value? This time, we subtract 1.464 with the estimate. And for 97.9, what do we do with 103.81 to reach 104? We need to add 0.181. And continuing this, we're going to have this one. Now, a linear regression is expected to have a mean or an average residuals of 0. And that the residuals must be normally distributed. Which means that when you try to put a histogram out of this, it must form a normal distribution. Now, since a while ago we said that for a patient with MCV of 87.8, the estimated hemoglobin is 136.9166. Let's estimate now the hemoglobin of a patient with MCV of, let's say, 88.8. So substituting this value again as the value of x sub 1, ignoring the epsilon, we're going to have 133.63970. Now, what do you notice here? It is shown in this example that an increase of 1 unit in the MCV, meaning from 87.8 to 88.8, the estimate of the hemoglobin decreases from 136.91 to 133.6397. This shows that a 1 unit increase in the MCV decreases the value of the hemoglobin by 3.277. In other words, when we increase this value up by 1, the tendency is this value will decrease by 3.277. And that is actually the one that's represented by the slope. So this value tells us that a 1 unit increase in x sub 1 decreases the value of y by 3.277. Decreases is because since this is negative. If this is positive, then y will increase. Thus, we may write this as it is evident that for patients who develop anemia, their MCV is negatively correlated with hemoglobin. Note that this is the result of the Pearson R, which shows that 1 FL increase in MCV decreases the hemoglobin at an average by 3.28. Now, this is the one which is your beta 1 estimate. Now, what I want to emphasize here is that when you perform a correlation, don't stop there. If the null hypothesis was rejected in the correlation, proceed with a linear regression. Because a correlation would simply imply that an x increase will decrease the value of y, but it doesn't quantify anything. The linear regression will tell you that an increase in x will decrease in the value of y by this quantity. Now, I'll show how to perform correlation and simple linear regression using R. Now, all you have to do is to open the file HGBMCV.RData. So, consider here that, again, your null hypothesis is that hemoglobin and MCV are not correlated, and your alternative is that hemoglobin and MCV are correlated. Now, let's view the data. So, here we have the actual data, which are the hemoglobin and the MCV. We may produce a scatter plot using the plot function. And further, we may label the x-axis and the y-axis using the x-lab equals and the y-lab equals options. All you have to do is to add x-lab equals and then the label of the x-axis, in this case MCV, then comma, y-lab equals and then the label in the y-axis, in this case HGB. So the scatter plot will just label its x and y axis. Now, to perform the correlation test, all you have to do is to perform the core.test function. And then in the end, you have the method equals C and then Pearson. Then press enter. We're going to see the correlation test result. Now, what you must notice here is that it's exactly the same value that we computed a while ago, in which the value of R is negative 0.903, and with test statistic T as negative 5.96, DF of 8, and the p-value which is 0.0003. Moving on with the simple linear regression, all you have to do is to perform the LM function. LM stands for linear model. Then the variable, which is y, and then the tilde, which separates the y and the x. So after tilde, we have the MCV, and then the file name. Now, the regress here is just an object name. You may choose any name. It's up to you. And then let's see the result by typing regress. Here we see the values of the y-intercept of 424.633 and the coefficient for MCV, which is negative 3.277. Thus, we may see that our equation is y equals this value plus this one times the MCV or x sub 1 plus some error term. Now, if you want to see that line on the scatter plot that we created a while ago, all we have to do is to use AB line. So A here is the y-intercept and B here is the slope. So what this code tells us is that I'm going to get the y-intercept from the regress output and I'm going to get the slope from the regress output as well. So while the scatter plot is open, we may put AB line, and it will show the line that best fits the scatter plot. Now further, we may use summary, parenthesis, then the object name, in that case regress, to show the complete linear regression results. Now what are these results for? Let's interpret all the results in this output. So the first one, let's have this one, the multiple r squared. Now multiple r squared is simply the square of the Pearson r. So note that the value of r that we computed a while ago is negative 0.903. Now squaring that value, we have 0.8162, which is this value. Now let's recall that r, which is the Pearson r, it tells you the magnitude and the direction of the relationship of x and y. Now, r squared, on the other hand, is what we call the coefficient of determination. In simple linear regression, or a univariate linear regression, is the square of the Pearson r. So again, the square of the Pearson r here is 0.8162, which tells us that it's the proportion of the variation in y that is explained by x. So in other words, 81.6% of the variation in y, which is the hemoglobin, is explained by the variation in x, in this case, the MCV. It tells us that 81.6% of the variation in the hemoglobin is explained or contributed by the MCV. Or in other words, 81.6% of the hemoglobin is because of the MCV. Now, what happened with 18.4% to complete the 100%? Now, 18.4% is due to errors. So again, this tells us that 81.6 of the hemoglobin is contributed by the MCV. And the remaining 18.4% is due to errors. Note that r squared is not a measure of accuracy, but rather it's a measure of how much y is explained by x. Moving on, let's have this one, the F statistic. Now, the F statistic here is a result of an analysis of variance. In simple linear regression, we have beta 0 plus beta 1 x1 plus error term. Now, what ANOVA tests here is simply the slope. So, given this estimate, is beta 1 really 0 or beta 1 not equal to 0? Now, later, when we proceed with multiple linear regression, we're going to have beta 2. We're also going to have beta 3, and so on. Now, the ANOVA will tell whether all the betas are equal to 0. So in simple linear regression, it's just this one. But in multiple linear regression, the ANOVA tests whether beta 1 and beta 2 and beta 3 and all the betas are all 0. While the alternative is that at least one beta is not 0. So in other words, the ANOVA will just tell you whether the coefficients are 0 or not. Why do they have to do this? Or why do we have to test using the ANOVA? It's simply because we want to determine whether a change in x will really change a value of y. Remember that the beta is the change in y for every 1 unit increase in x. Now, the ANOVA will tell you whether really there is a change or not. Now, given this null hypothesis and alternative hypothesis here, since the p-value here is less than 0.05, then we're going to reject the null hypothesis and claim that there's sufficient evidence that beta 1 is not 0. Or in other words, when we get the entire population data, it is unlikely that the slope is 0. So we can conclude that x sub 1 or MCV is really a contributor in y. Note that if the p-value is greater than 0.05, we will not reject the null, which implies that we have a reason to believe that beta 1 is 0, indicating that if the slope is 0, what happens? If this is 0, what happens? Any change in x will not change the value of y. In other words, x is not a contributor of y. Now, the coefficients here, we have beta sub 0 hat as 424 and beta sub 1 hat as negative 3.27, indicating that our linear regression model is 424.633 minus 3.277 x sub 1 plus the epsilon. Now, why do we have to have this p-value here? That p-value implies that since our beta 1 estimate is 3.277, your null hypothesis implies that beta 1 is 0, alternative, beta 1 is not 0. So it's like the ANOVA a while ago. But again, the ANOVA later will not be the same as this when we speak of the multivariate or the multiple linear regression. So in this case, it's exactly the same as the ANOVA in simple linear regression context. So since the p-value is less than 0.05, we're going to reject the null and conclude that there is sufficient evidence that beta 1 is not 0. Again, this implies that when we collect the entire population data, it's unlikely that your beta 1 is 0. So this is our conclusion. So we may say that, again, MCV is a contributor of hemoglobin. By how much? 1 unit increase in the MCV decreases the hemoglobin by 3.277, which is the same result that we got a while ago.